Okay, I'm going to prove that a function being continuous topologically is equivalent to the direct image of the closure being a subset of the closure of the direct image. A function being topologically continuous usually means that for all b open, the inverse image of b is open, but the same definition works with closed sets, so that's the definition we use. Let's begin the proof. The implication part. So if this is true, we have to prove this is true. So assuming f continuous, we want to prove direct image of the closure of A is a subset of the closure of the direct image of A. Now, every time we have a direct image on the left side of an inclusion, we can pass the direct image to the other side, like this. And to clarify, the reason why is because direct image of A is included in B is equivalent to A is included in the direct image, in the inverse image of B. It's actually related to clA connections, but no need to worry with that. We just take it for granted. Now we do this just because inverse images are obviously better behaved in topology. Okay, so we want to prove this one. We want to prove this in yellow. Now, if we erase this, this would be true. So the statement is almost true. Okay, because another fact we know is that A is contained in the direct of the inverse of A. Okay. So we know this contains A. Let's try to do something with this. We know this is contained in the inverse image. Okay. So we can make this smaller and we'll obtain something smaller. So the closure of the direct image of A is smaller than the direct image of A, right? So this is an inclusion here. And now we already know this is true, right? So if you observe, this is almost what we want, the diagonal. That is, what we want is almost this. A is a subset of the inverse image of the closure, direct image of A. And now we can just apply the closure on both sides because we want to make this into this, right? And we obtain closure is a subset of the closure of the inverse image of the closure of the direct image of A. And this is where continuity comes in. We know that this is a closed set because it's an inverse image of a closed set. This is a closed set because it's a closure. And so this is equal to this. And the inverse image of the closure of the direct image of A is going to be a superset of the closure of A. Sorry. Okay, like we wanted. Okay. Which is what we wanted to prove. Okay. Proof on the other side. So assuming this, we want to arrive at the fact that f is continuous. So we want to prove if B is closed, then inverse image of B is closed. Okay, so let B be closed. Then we want to analyze whether f inverse of B is closed. And that's the same as the closure of f of B being equal to B, right? It's the same thing, because the closure of closed sets is closed, is the set itself, and that ends up implying that a set is closed exactly when the closure is equal to itself. And this is a condition to be closed. And so obviously to apply our hypothesis, our assumption, this set has to be on the domain of f, and it is, so we apply it. And so inverse image of the closure of inverse image of B is a subset of the closure of the direct image of the inverse image of B. Okay. Now again, this implies we pass the direct image on the left of an inclusion to the other side. Sorry, accidentally here I wrote the inverse image. I meant to write the direct image. Okay. This implies, so note here, this is redundant. We take the inverse and then we just map it back. So this is going to be equal to, so this is going to disappear. Sorry. That's wrong, but it's somewhat true. But we don't need to go there. Okay. This is smaller than B. Therefore, the closure is also smaller. So this is smaller than B, which is equal to B, since B is closed. Okay. So we get our diagonal here that I'll just stress. Okay, which implies, so I'll rewrite it. Closure inverse B, is included in B, and we can do the pass to the other side trick. It's actually equivalent, but yeah. So the closure of, oops, I messed up. Wrong direction of the arrow. So the inverse image of B, which is the same thing as saying that the inverse image of B is closed. Okay, that's all we wanted. Done. These are the two proofs. And proved one direction, the other direction. And so the equivalence is proved.